calculate the vibrational energy levels of an HCl molecule assuming the force constant to be 516 Newton per meter. In this problem, we have to find out the vibrational energy levels of HCl molecule. The force constant is given. What is the expression for vibrational energy levels? If we take the anharmonic oscillator model, it is E nu is equal to nu plus half omega E bar minus nu plus half whole square omega E bar xc centimeter inverse, where nu is the vibrational quantum number and xc is the anharmonicity constant. Take the mass of hydrogen mH as 1 atomic mass unit and mass of chlorine as 35.5 atomic mass unit. Now let us find out the reduced mass mu, that is mH into mcl by mH plus mcl into 1.66 into 10 raised to minus 27 kilogram. Here mass of hydrogen atom is 1 AMU and mass of chlorine is 35.5 AMU. Therefore mu is equal to 1 into 35.5 divided by 1 plus 35.5 into 1.66 into 10 raised to minus 27 kilogram. And this is equal to 1.61 into 10 raised to minus 27 kilogram. This is the reduced mass mu. To find out the vibrational energy level, we have to evaluate omega E bar. What is omega E bar? This is equal to 1 by 2 pi c into root of k by mu. K is the force constant which is given in the problem as 516 Newton per meter. Therefore, what is omega E bar? This is 1 by 2 pi c root of 516, that is k by mu is equal to 516 divided by 1.61 into 10 raised to minus 27. Omega E bar equal to 1 by 2 into 3.14 into 3 into 10 raised to 8 square root of 516 divided by 1.61 into 10 raised to minus 27, and this is equal to 300,490.685 meter inverse. That is omega E bar, that is equal to 3004.91 centimeter inverse. Thus we have evaluated omega E bar. Now let us find out the vibrational energy levels. The vibrational energy levels of an HCl molecule using anharmonic oscillator model is nu plus half omega E bar minus nu plus half whole square omega E bar xc. We have evaluated omega E bar as 3004.91 centimeter inverse. Therefore, the vibrational energy level E nu is equal to nu plus half into 3004.91 minus nu plus half whole square 3004.91 xc. What is the minimum voltage to be applied to an X-ray tube to produce X-ray of 1 angstrom? In this problem, we have to find out the minimum voltage to be applied to an X-ray tube so that we will get an X-ray of wavelength 1 angstrom. Here you have to use the formula. The minimum wavelength lambda minimum, that is equal to Hc by Ev, that is equal to 1242 by V nanometer. Therefore, the voltage is 1242 by lambda minimum Remember that here the lambda minimum should be in nanometer. Lambda minimum should be in nanometer. Given lambda is equal to 1 angstrom, therefore this is equal to 0.1 nanometer. Therefore the minimum voltage is 1242 by 0.1 volt, and this is equal to 12420 volt, or we can say V is equal to 12.42 kilovolt. The carbon monoxide molecule has a bond length of 0.113 nanometer and the mass of carbon 12 and oxygen 16 atoms are 1.99 into 10 raised to minus 26 kilogram and 2.66 into 10 raised to minus 26 kilogram respectively. Find the energy of carbon monoxide molecule when it is in the lowest rotational state. In this problem, we have to find out the rotational energy of carbon monoxide molecule when it is in the lowest rotational state. The expression for rotational energy level Ej is equal to Bj into J plus 1 centimeter inverse, where J is equal to 0, 1, 2, 3 are the rotational quantum numbers. For the lowest rotational state, we know that the value of the rotational quantum number J is equal to 0. Therefore, the energy of CO molecule in the lowest rotational state becomes B into 0 plus 1, that is Ej is equal to 0 centimeter inverse. The next problem is the rotational constant for carbon monoxide molecule is 1.921 centimeter inverse. Find the ionic bond length of the molecule. Mass of the carbon and oxygen atoms are 19.92 into 10 raised to minus 27 kilogram and 26.56 into 10 raised to minus 27 kilogram. In the present problem, the rotational constant for carbon monoxide molecule is given. We have to find out the bond length. Here you have to use the relation. The rotational constant B is equal to h by 8 pi square IC, where I is equal to mu r square. It is given that B is equal to 1.921 centimeter inverse and that is equal to 192.1 meter inverse. Now what is the moment of inertia I? That is equal to h by 8 pi square BC. This is equal to 6.626 into 10 raised to minus 34 divided by 8 pi square into 192.1 into 3 into 10 raised to 8, and that is equal to 145.62 into 10 raised to minus 48 kilogram meter square. This is the moment of inertia I. We have to find out the bond length. Before that, let us find out what is the reduced mass. Mu is equal to mass of carbon into mass of oxygen divided by mass of carbon plus mass of oxygen. Here all the masses are given in kilogram. So let us find out the reduced mass. Mass of carbon atom, that is equal to 19.92 into 10 raised to minus 27 kilogram. Mass of oxygen atom is 26.56 into 10 raised to minus 27 kilogram. Now the reduced mass mu is equal to 19.92 into 10 raised to minus 27 into 26.56 into 10 raised to minus 27 divided by 19.92 plus 26.56 into 10 raised to minus 27, and this is equal to 11.383 into 10 raised to minus 27 kilogram. This is the reduced mass. Now we have the reduced mass and moment of inertia. Now we can calculate the bond length using the equation R is equal to root of I by mu. I by mu. This is equal to 145.62 into 10 raised to minus 48 divided by 11.383 into 10 raised to minus 27, and that is equal to 113.11 into 10 raised to minus 12 meter. That is the bond length. R is equal to 1.13 angstrom. The next problem is OH radical has a moment of inertia 1.48 into 10 raised to minus 47 kilogram meter square. Calculate its internuclear distance. Also calculate its angular momentum and angular velocity for J is equal to 5. In the present problem, OH radical is given. We have to calculate its internuclear distance and angular momentum and angular velocity for J is equal to 5. If J is the rotational quantum number, then angular momentum L is given by root of J into J plus 1 h bar. What is the reduced mass here? It is mass of oxygen into mass of hydrogen divided by mass of oxygen plus mass of hydrogen. That is equal to 16 into 1 divided by 16 plus 1 into 1.66 into 10 raised to minus 27 kilogram. And that is equal to 15.623 into 10 raised to minus 28 kilogram. Here the mass of oxygen is taken as 16 and the mass of hydrogen is taken as 1 AMU. Now what is I? Moment of inertia is given in the problem as 1.48 into 10 raised to minus 47 kilogram meter square. Therefore the bond length R is equal to root of I by mu, and that is equal to root of 1.48 into 10 raised to minus 47 divided by 15.623 into 10 raised to minus 28, and this is equal to 97.33 into 10 raised to minus 12 meter. That is R is equal to 0.973 angstrom. That is the bond length is 0.973 angstrom. Now let us find out the angular momentum for J is equal to 5. L is equal to root of J into J plus 1 h bar. Here J is equal to 5. Therefore L is equal to root of 5 into 6 h bar, that is equal to root of 30 h bar. That is angular momentum is root 30 h bar. The value of h bar is, let us substitute the value of h bar. Value of h bar is 1.054 into 10 raised to minus 34. Therefore the angular momentum is root 30 into 1.054 into 10 raised to minus 34. That is equal to 5.77 into 10 raised to minus 34 kilogram meter square per second. Now let us find out the angular velocity omega. That is equal to L by I. We have find out L, we know what is I. Therefore omega is equal to L by I, that is 5.77 into 10 raised to minus 34 divided by I is 1.48 into 10 raised to minus 47. That is the angular velocity is 3.90 into 10 raised to minus 13 radian per second. The next problem is, for the exciting light of 4358 angstrom, the Raman spectrum of benzene shows Raman lines of delta nu is equal to 608, 846, 995, 1178, 1599, 3064 centimeter inverse. At what wavelength would these Raman lines appear if benzene is irradiated with a monochromatic light of 5461 angstrom? In the present problem, Raman shift is given For the exciting light of 4358 angstrom, we have to find out the position of the Raman line, the wavelength corresponding to the new position of the Raman line if we change the exciting light to 5461 angstrom. First, let us find out the wave number corresponding to the new excited light of wavelength 5461 angstrom. That is, nu bar is equal to 1 by 5461 into 10 raised to minus 10, and that is equal to 18,311.67 meter inverse, and that is equal to 18,311.67 centimeter inverse. This is the position of the Rayleigh line corresponding to the excitation 5461 angstrom. Now let us find out the position of the Stokes Raman line if the excitation wavelength is 5461 angstrom. Already the Raman shift is given. Therefore, the position of the Stokes line corresponding to the shift of 608 centimeter inverse is 18,311.67 minus 608, that is 17,703.67 centimeter inverse. In this problem, we need to find out the position of the Raman line corresponding to the wavelength. Now what is lambda? Lambda is 1 by nu dash minus delta nu bar, that is 5648.5 angstrom. Now corresponding to the shift 846 centimeter inverse, the position of the Stokes line is 17465.67 centimeter inverse, and the corresponding wavelength is 5725.552 angstrom. Now corresponding to the shift 995 centimeter inverse, the position of the Stokes line is at 17316.67 centimeter inverse, and the corresponding wavelength is 5774.78 angstrom. Now for a shift of 1178 centimeter inverse, the position of the Stokes Raman line is at 133.67 centimeter inverse, and the corresponding wavelength is 5836.46 angstrom. And if the shift is 1599 centimeter inverse, the position of the Stokes Raman line is at 16712.67 centimeter inverse. The corresponding wavelength is 5983.49 angstrom. And if the Raman shift is 3064 centimeter inverse, the corresponding position of the Stokes Raman line is at 15247.67 centimeter inverse, and the corresponding wavelength is 6558.38 angstrom. The next problem is the microwave spectrum of cyanide CN shows a series of lines separated by 3.7978 centimeter inverse. Calculate the internuclear distance. We know that in rotational spectra or microwave spectra, the spacing between adjacent rotational lines is 2b, where b is equal to h by 8 pi square IC, where I is the moment of inertia, and the bond length is given by root of I by mu, where mu is the reduced mass. It is given that the spacing between the rotational lines 2b is 3.7978 centimeter inverse. Therefore, the rotational constant b is 1.8989 centimeter inverse, that is equal to 189.89 meter inverse. Now let us find out the reduced mass mu. It is equal to mass of carbon into mass of nitrogen by mass of carbon plus mass of nitrogen. Take mass of carbon is equal to 12 atomic mass unit, and mass of nitrogen is equal to 14 atomic mass unit. Then the reduced mass is 12 into 14 divided by 12 plus 14 into 1.66 into 10 raised to minus 27 kilogram, or mu is equal to 1.07 into 10 raised to minus 26 kilogram. This is the reduced mass. Now let us find out the moment of inertia I. I is equal to h by 8 pi square bc. This is equal to 6.626 into 10 raised to minus 34 divided by 8 pi square into b is 189.89 into 3 into 10 raised to 8, and that is equal to 1.4746 into 10 raised to minus 46 kilogram meter square. This is the expression for moment of inertia. Now we can calculate the internuclear distance. R is equal to root of I by mu. R is equal to root of I by mu, and this is equal to square root of 1.4746 into 10 raised to minus 46 divided by 1.07 into 10 raised to minus 26. And the value is 117.39 into 10 raised to minus 12 meter, or R is equal to 1.17 angstrom. 1.17 angstrom. The next question is calculate the reduced mass and moment of inertia of HCl having bond distance of 1.27 angstrom. The atomic weights are 1.008 and 34.98 for hydrogen and chlorine respectively. Here, the reduced mass mu is equal to mass of hydrogen into mass of chlorine divided by mass of hydrogen plus mass of chlorine into 1.66 into 10 raised to minus 27 kilogram. I is the moment of inertia, that is equal to mu r square, where r is the bond distance. It is given that the mass of hydrogen, that is equal to 1.008 AMU, and mass of chlorine is equal to 34.98 AMU. Therefore, the reduced mass mu is equal to 1.008 into 34.98 divided by 1.008 plus 34.98 into 1.66 into 10 raised to minus 27 kilogram. That is, the reduced mass mu is equal to 1.626 into 10 raised to minus 27 kilogram. Now let us find out the moment of inertia I, that is equal to mu r square. Mu is equal to 1.626 into 10 raised to minus 27. In the problem, R is given as 1.27 angstrom. That is 1.27 into 10 raised to 10 raised to minus 10 meter. Therefore, I is equal to 2.622 into 10 raised to minus 47 kilogram meter square. The next question is calculate the strength of the magnetic field required to give processional frequency of 100 MHz for oxygen 17 nucleus, given Gn is equal to 0.757, mu n is equal to 5.051 into 10 raised to minus 27 joule per Tesla, I is equal to 5 by 2. Here we have to use the resonance condition for NMR spectrum. H nu is equal to Gn mu n B0, where Gn is the nuclear G factor and mu n is the nuclear magneton, which is given in the problem. What is B0? This is H nu divided by Gn mu n. This is equal to 6.626 into 10 raised to minus 34 into frequency is given by 100 into 10 raised to 6, that is 100 megahertz, divided by Gn is given in the question as 7.757 and mu n is also given as 5.051 into 10 raised to minus 27. Therefore, B0 is equal to 17.33 Tesla.